Very good morning, one and all present here. Today we are going to discuss about governance and its working principle. So while seeing the syllabus, so we have different type of governance and like a centrifugal governor, gravity controlled governor, spring controlled governance, and their characteristics. We are going to discuss on today's topic. So first we should know the introduction, how what is meant by governor. So the function of the governor, that is to regulate the mean speed of an engine when there are variations in the load. So when the load on the engine it increases, the speed automatically decreases. Therefore, it becomes necessary to increase the supply of working fluid. On other hand, when the load of the engine decreases, the speed increases, and thus less working fluid is required. So the purpose is when the load increases, the speed automatically decreases. When the load decreases, the speed automatically increases. So the working fluid should be regulated. For that purpose, we are using governor. So the governor automatically controls the supply of the working fluid to the engine with the varying load conditions and keeps the mean speed within certain limits. So the flywheels, the speed variations caused by the fluctuation of engine turning moment during each cycle of the operation. So it does not control the speed variations caused by a varying load. So the governors which are classified as a centrifugal governor, which are classified into two types. One is pendulum type and another one is loaded type. So the pendulum type again classified as watt governor. So this loaded type again classified as dead weight governor, or we can say that as a gravity controlled governor, and another one is spring controlled governor. Again, this dead weight governor classified into two types, one is Porter governor and Proel governor. This Proel governor again classified as this Hotnell governor, hot tank governor, Wilson Hotnell governor, Pickering governor. So that spring controlled governor classified into four categories. So this centrifugal governor, that was based on balancing of centrifugal force of the rotating balls by equal and opposite radial force, that is called controlling force. We will call that as controlling force. So here it consists of two balls of equal mass. So here in the centrifugal governor we have a governor ball that we can call as fly balls. So these balls revolve with the spindle which is driven by engine through the bevel gear. The sleeve which is connected by the belt crank lever to a throttle valve. The supply of the working fluid decreases, so the sleeve will rises and increase when it falls. So here you can see the components or the parts which are available in the centrifugal governor. We have arms and we have fly balls which is attached with the spindle by means of links with the help of links and as well as arms. So here we have a sleeve attachment along with. So here we have an additional setup, that is a bevel gear which is used to give a moment to the sleeve along with the sleeve that is connected with the belt crank lever. So here we have a supply of working fluid along with the throttle valve. When the flow is required, this throttle valve will open and the fluid flow will be happening so that the speed will be maintained. When the fluid flow is not required or minimal weight is there, means to maintain a speed, the throttle valve will be closed and the fluid flow will be controlled. And the terms which are used in the governor, that we should understand. Now in the diagram you can see, right side diagram, the h that denotes the height of the governor. So that is nothing but the vertical distance from the center of the ball to the point where the axis of the arms are produced to intersect the spindle axis. So it is usually denoted by h. And coming to equilibrium speed, it is a speed at which the governor ball arms are completely equilibrium and the sleeve does not tend to move upward or downward motion. So the equilibrium speed means that will maintain a certain position. There won't be any upward movement and downward movement. And coming to this mean equilibrium speed, it is speed at the mean position of balls or the sleeve. So maximum and minimum equilibrium speed. The speeds at the maximum and minimum radius of rotation of the balls without tending to move either way are known maximum or minimum equilibrium speed respectively. So sleeve lift. So how much distance it was traveling. So vertical distance which the sleeve travels due to the change in equilibrium position. Next, coming to the spotter governor. It is a modification of watt governor when the central load attached. Here you can see in previous governor we don't have central load, but here we have a central load. So the load will move up and down in the central spindle. So this additional downward force increases with the speed of the revolution that is required to enable the ball to rise to any predetermined level. So here we can see the mass of the ball that is denoted by small m, that is in kg, and coming to w, because of that mass will have a weight that is in newton, that is m dot g, that is a gravity, and capital M, that is central load, mass of the central load that is in kg, again weight of the central load that is in newton, capital M dot g, again the radius of rotation that will be in a meter. And the notations which we can see in the right side diagram, that height already we have discussed, that is the height of the governor, that is in meter, and n, that is speed in balls, that is in rpm. So omega, that is angular speed in balls, that is radians per second, that is 2 pi n divided by 60 radians per second. Fc, that is centrifugal force acting on ball, that is in newton, m omega square into r. So this T1, that is force in arms, force in the arm in Newton, T2 force in link, that is in Newton, alpha, that is angle of inclination of the arm, so that makes with the upper link. So to the vertical direction, the upper link what is making angle, no, that is angle of inclination of the arm. So again this beta, that is downward due to the central load, the angle of inclination to the vertical, that we can say as lower link. So the forces which are acting on the governor, that we can calculate with the by means of this relationship. So that is n square is equal to m plus capital M by 2 into 1 plus q into 895 by h. So here the length of arms are equal. If in that case both the length of the arms are equal, means we will get tan alpha is equal to tan beta. So q is equal to tan alpha divided by tan beta, which is equal to 1. So here we can consider n square is equal to m plus capital M divided by into 895 divided by h. Suppose if the frictional force acting on the sleeve, that is in Newton, we have to add the force. So n square is equal to m dot g plus capital M dot g plus or minus f divided by 2 into 1 plus q divided by m dot g into 895 divided by h. So this positive signs dictate that sleeve that is moving upward and the governor speed increases, and the negative sign that is used to note down the sleeve moves downward. So here we have one problem. Here the length of the arm that is given, that is 250 mm, which is pivoted to the axis. Mass of the ball that is given 1 is 5 kg, and the central load, that is capital M, that is 30 kg, and the radius of rotation that is given, that is 200 mm during the maximum load, and 150 mm during the minimal rotation that is given. So R1 and R2 is given. So these all are the two conditions. So during maximum speed and minimum speed conditions are given. So maximum speed is denoted by n2 and the minimum speed that is denoted by n1. So during that the distance between the vertical to the mass of the central, the radius of the ball, center of radius of the ball, that is 150 and 200. So now we have to calculate the speed range of the governor. So to calculate using Pythagoras theorem, we can calculate this h1 distance, that is opposite side plus adjacent side, that is using that we can calculate. So from that you can see h1 is equal to, we will get a value of 0.2 meter, and similarly the speed for minimum condition that we can calculate. The formula already we discussed, that is n1 square is equal to m plus capital M divided by m into 895 divided by h. So we know the value of ball mass as well as the central load mass. Substitute those values and we can calculate n1 value, that is during minimum condition. And now to calculate this maximum condition, h2 value is missing. That can be calculated using the same Pythagoras theorem. So we'll get a 0.15 meter value, and again we can calculate the maximum speed, that is n2 square, using the relationship m plus capital M divided by m into 895 divided by h2. So h2 value we have calculated, and small m and capital values are known values, so we can substitute and calculate the n2 value. So the range of the speed of the governor can be calculated, that is n2 minus n1. So we'll get a value of 27.4 rpm. Now to calculate the speed range, while considering the frictional force, already we told when it is moving upward, the minimum speed is given. So moving upward means negative sign, moving downward means positive sign. So we have to add the frictional force acting on the sleeve, that can be considered. So n1 square is equal to m dot g plus capital M dot g minus f, that is nothing but the frictional force which is acting on the sleeve downward and acts upward on the minimum speed. So substitute those values and we'll get a n1 value, and another one in the force acts upward means positive, downward means positive. So you'll get a speed of maximum speed of n2. So we can calculate the speed range of the governor, that is n2 minus n1. So another problem, here we have a length of arm, that is 300 mm, and the upper arm is pivoted to the rotation. So the sleeve at the distance of 40 mm from the axis, the distance is given, and the mass of the sleeve, that is 40, and ball weight is given, and the ball rotation, that is 200 mm, equilibrium speed is given, and the frictional force is given. So h value we can calculate using Pythagoras theorem. So h, what you will get now, 224. From that we can calculate tan alpha and tan beta using tan, relating this triangle BPG and BDF, relating these two triangles with the tan alpha and beta. We can calculate this value, and we can calculate q value, that is 0.705 we'll get. And now that n2 speed we can calculate, that is maximum speed we can calculate, that is m plus m by 2 into 1 plus q into divided by m into 895 divided by h. So all the values are known value, you can calculate n2. At same time you can calculate n1 also. So here the frictional force is given in the problem, so consider the force whether it is acting upward or downward, and we can calculate the range of speed. So now pronal governor. So here we can see the difference, that is the balls fixed at B and C, there is some extension from the F and G. So the extension arm is from DF and EG. So this arm we can call the extensional links. So based on that extensional links, we can have a relationship, that is n square is equal to Fm divided by Bm, and into m plus capital M divided by 2 into 1 plus q divided by m into 895 divided by h. So this alpha, when it makes an angle of alpha is equal to beta, then q we can consider that as 1. So now both are pivoted in the same axis, means alpha is equal to beta, which will make same angle. So n square is equal to fm divided by bm into m plus m. This 1 q becomes 1, so that 1 plus 1 becomes 2. So these two gets cancelled. So m plus capital M divided by m into 895 divided by h will get a final expression. So in that we have one problem. The Proel type has each arm 250 mm. So the arm has 250 mm. The pivot of upper arm and lower arm, which is 25 apart from the axis. The central load is given, and the mass of the ball is given. So the governor sleeve is in mid position of the extension arm, and rotation of masses, that is 75 mm radius distance. Vertical height of the governor is given, that is 200 mm. So now they asked to calculate the governor speed when it is 160 rpm in the mid position. The extension link length and tension of upper arm we have to calculate. So the length of the extension link we have to calculate. So the relationship, we know that n square is equal to fm divided by bm into m plus capital M divided by m into 895 divided by h. So this problem can be solved using instantaneous method or resolving force method. So usually we will prefer instantaneous method, that will be simple than the solving using resolving method. So here alpha is equal to beta, so that we can, due to the mid position, we can consider that q as 1. So now we'll get a length of bm, which is the missing value. So from that we can calculate the length of extension link length, that is bf is equal to, from the total length, if you subtract this fm length, you will get that bf value. And the tension in the upper arm, that can be calculated using the Pythagoras theorem. So that pk value is missing, so that you can calculate the pk value, that is 200 mm. Now you can relate this triangle PEFK with cos alpha, so that we'll get a value of 0.8. Now the tension equation, we can solve that equation and we can calculate the T1 value. And coming to this Hartnell governor, which is comes under spring loaded category, so which consists of two bell crank lever pivoted at the points O dash comma O to the frame. Okay, so the frame is attached to the governor spindle and therefore rotates within. So each lever carries a ball at the end of the vertical arm OB and the roller arm at the end of the horizontal arm OR. So helical spring in compression provides equal downward force on the two roller through the collar of the sleeve. So now coming to the spring force may be adjusted by screwing a nut up or down on the sleeve. So now here we have two conditions. One is minimum position condition and maximum position condition, and the spring forces, all those things we have to consider for this governor axis, from the governor axis. So here the notations are given. Already we know that small m, that is mass of each ball, that is in kg, and capital M, that is mass of sleeve, that is in that is also in kg. R1, that is minimum distance from the rotation axis. Okay, and that should be in meters, and R2, that is maximum radius from the rotation axis, that is also in meters. Omega 1, that is minimum angular speed, we can say, that should be in radians per second. And omega 2, that is angular speed of the governor, that is maximum during maximum condition, that is also radians per second. And S1, that is spring force exerted to the sleeve, that is in omega 1, that is Newton. And force, S2, that is spring force exerted to the sleeve, that is at omega 2, that is also in Newton. Now coming to the centrifugal force, omega 1, that is calculated m omega 1 square into r1. Fc2, that is centrifugal force at omega 2, that is also in newtons, that is m omega 2 square into r2. So yes, that is stiffness of the spring, or the force required to compress the spring by 1 mm. X, that is the vertical or ball arm of the lever in meters. Y, length of horizontal or sleeve arm of the lever in meters. So R, that is a distance of the fulcrum O from the governor axis. So this is the summary we can derive, that is S is equal to S2 minus S1 by H. So this can be written as the centrifugal forces, relating with centrifugal forces, 2 times of Fc2 minus Fc1 divided by R2 minus R1 into X by Y the whole square. So here, by considering the intermediate position, we'll have the minimum, we'll have a minimum and intermediate position, that is S is equal to 2 times of Fc minus Fc1 divided by R1 R minus R1 into X by Y the whole square. So during the maximum position, if you want to calculate, so that from Fc2 by minus Fc divided by R2 minus R into X by Y the whole square. So relating from the equations 3 three equations. Writing the three equations, final expression will get FC2 minus FC1 into R2 minus R divided by R2 minus R1. So this problem Hartnell governor that is having a centrifugal sleeve which is during two different speeds, one is minimum and the maximum speeds n1 and n2 value is given, and sleeve height is given, and the ball weight and the arm weight is given. So we have to calculate the load on the spring at the lowest and highest equilibrium speed and stiffness of the spring we have to calculate. So to calculate that we have to know the value of R2, FC2 value we have to calculate, so that we can calculate this S2 and S1, that is a force which is acting on the arm that we can calculate during lowest and highest speed. The density of the spring that can be calculated as S2 minus S1 divided by H, that is the value. And if you want to calculate the sensitivity at a governor, that is difference between the maximum and minimum equilibrium speed of to the mean speed, that is sensitivity of the governor, and stability, we can say that is said to be stability when the every speed within the working range there is a definite configuration. So when the speed increases, the belt governor balls must increases. So the governor is said to be unstable if the radius of rotation decreases as the speed increases. Isochromous governors, we can say that as when equilibrium speed is constant, we can call as that isochromous governor. And coming to hunting, so it is said to be hunt if the speed of the engine fluctuate continuously above and below the mean speed, and some controlling forces that are there, that we can say that as the governor running at a steady speed, inward force acting on the rotating balls is known as controlling force. Thank you.